to squeeze 2 lectures in today. Or probably not going to make it that much, but. So, we're looking at 1.8 Introduction to Linear Transformations, 1.9. Matrix of linear transformation. Okay. So we take one more slight step in the abstract direction today. Let's just talk about functions in general at first. So this is a particular class of mathematical objects that we have a lot of experience with. Most commonly, or you probably have the most experience with functions from real numbers to real numbers. So this is a sort of a string of symbols that I've written on the board, and this is what they mean. You've probably seen this before, so this may be just review. So this first thing, I'm referring to the function as f, so this is the name of the function. This right here specifies the set of things that are valid as input to the function. Right? A function is merely something that takes an input and gives you an output. That's it. So there's nothing more to the definition of a function than that. This is the set or collection of valid inputs. And this was known as the domain. And this is the set in which all outputs reside. So this is the world in which we will be expecting outputs to come from. And this is called, you may have heard range. We're going to, this class, use the term codomain. Range is going to be reserved for something else. So when we give the definition of a function, we have to be able to say, well, back in the day, you might have said something like this: f of x is the prototypical example, f of x equals x squared, where it was implicit because the only types of numbers you'd ever talk about in your class were real numbers, that the input was going to be a real number, and based on the formula that you gave for the output of the function, the output was also going to be a real number. So when we talk about these things more abstractly, we need to know what the input, where the input is going to come from, and where it's going to go. And so this bit of the function, what would we call this? This is sort of, we're declaring what the function is. This is the type of function. So this specifies what kind of function it is. And then we can think about all possible functions that go from real numbers to real numbers. That would be all functions of this type. Okay. I want to talk about another example of this. This is kind of a silly example, but let's say, let's give this a new function. We'll call it g. So this new function g is going to be a function that goes from the set a, b, c. You see I've used the curly braces to specify literally what the set is. So I said it is the set of these 3 elements. And it's going to have as its codomain the set circle, square, triangle, with 3 things in it. Let's make it a little exciting. Let's just say there are 2 things in it. Because you might have thought, well, what are all the possible maps from one set to the other, from this one set to the other. There are lots of possible definitions. One of them, let's call this first one. Yeah. G of A and G of B and G of C were me putting these inputs into the function. They're all equal to square. So this is a constant function. Every input has the same output. In this case, nothing in the domain of G gets mapped to triangle. Okay. Not necessarily a good thing or a bad thing, just a thing. This is just one thing that we can say about this function. There are things in its codomain that it does not get mapped to. So let's talk about, let's write it like this. G of, and I'm going to write as input this whole set. So what do I mean by this? If I put this set in as input, what I'm implying by writing this is that I want the set of all possible outputs that I can get from this. So this is, I put as the input the entire domain, and what I will get as output is a set of all possible outputs. There's only one possible output, and it is square. So we'll refer to as the set of all possible outputs will be called the range of the function. I'll abbreviate function. Okay, are there any questions about this? So just some basic definitions. Hopefully a lot of this is just review. And maybe there might be a little confusion. In calculus, we did often refer to all possible outputs of a function as its range. Because we never really needed to specify what the output codomain was most of the time. We were dealing with formulas like this, or possibly we were dealing with formulas in terms of vectors, in which case we might have vector outputs, things like that. But we really never had to specify the codomain. So we're going to call the codomain just some set, and it's where we're going to look for outputs. That's just going to be the definition. Sometimes it might be useful to say that, for example, G is a function that takes things from this particular domain and outputs things in this codomain. But we don't say what the function is. It's just some function that does that. And that's one particular situation in which this kind of notation is useful. Okay, now, let me look at the book. So the book refers to this as the uniqueness and existence problem. I'm going to go ahead and I'm going to give you the terminology for this. So this is going a little bit beyond what the book talks about, but it's useful to know these terms anyway. So let's say this function has the property that G of A equals G of B. It maps A and B to the same thing, but A is not equal to B. A is not equal to B. So in the terminology of the book, this is again, it's a uniqueness or existence question. different inputs don't give unique outputs. So if, so let's say, if a function f is such that f of a equals f of b implies that a equals b. And f is said to be the terminology we used in calculus was the English terminology, 1 to 1. The often preferred French terminology coming from the French mathematicians is injective. So when you look at what things map to from your domain into your codomain, then two things, if they map to the same thing, then they must have been the same thing. If two things are different, another way to state this. In other words, this is called the contrapositive of the statement. If we're saying this being true implies this being true, then what's another way to state that? This not being true implies that this is not true. Because if it were true, it would have implied the opposite. So in other words, we can say that if A does not equal B, which is the opposite of this statement, the opposite of saying A is equal to B is saying it's not equal to B. This will imply that f of A is not equal to f of B. So this is called taking the contrapositive. I should write that. A bit of logic terminology. Particularly if you're a math major. Is anybody in here a math major? I know there are some in the class, so maybe people listening at home will be raising their hands right now. But yeah, if you go on to take any proof-based courses, there will be a bit of proof, but not much in this class. Then this is the sort of thing that we just want to know. So this is another way to state that. It's one-to-one, or I'm just going to say it's injective. So it takes things. Are you a math major? Oh, okay. No math majors in here. Think about it. I get $1 every time I tell you to consider putting the math program.
I used to be a math major.
And then you took an arrow to the knee. Okay, I'm gonna. And what happened?
I decided I liked programming then.
Oh yeah, programming is fun. Yeah. Okay. Now, this is okay. Let's state the other property. Oh, underline it. So this is the property of the function. That will be interesting. Is it injective or is it not injective? So G here was not injective. Right? We agree on that. What's another consequence of this? If I map forward from stuff in my domain to stuff in my codomain, and I try to find an inverse, I try to go backwards, I can't do it, right? Because I won't know which input to go back to, because two of them could have gone to the same one. It's not injective, so it doesn't have an inverse. Say about that? Oh, we saw this as an example. In calculus, we saw this. When we looked at inverse trig functions, it was impossible to get, I don't know what that function is. There we go. Looks like sine, right? And you can see it's not injective. It maps multiple things to the same point, particularly 0. You see that it maps things to 0 every every pi. Every time you go around pi, go another pi forward, you get another 0. So we couldn't map backwards, but if we instead modified the sine function, the sine went from, we call this a function from R to R, right? We could have called this a function from R to -1, the interval from -1 to 1, closed interval, including the endpoints. The codomains, the two codomains wouldn't matter. We would technically consider these to be different functions because they have different types. So this is the sign that goes from R to R, this is the sign that goes from R to -1, 1. Does that distinction make sense? The type of this function is something that's intrinsically connected to the function itself. Right? That's the way we think about these things. If we have functions with two different types, even though we call them the same thing, they are not the same thing. So that's an important distinction. Now, let's make another modification to the sine function. Let's call this sine, put a hat on it. So this sine goes from, oh, what would it be? From here to here. So that's negative pi over 2 to pi over 2. R, for example. So this was the restriction of the sine function, and it made it a one-to-one function. It made it an injective function. And then we can talk about the inverse, which was arc sine, or ARC sine, or for the people who weren't being careful and noticing that this is not the inverse of sine, it's the inverse of this restricted sign. And we would some inverse. Bad style, bad form, but they do. Okay. So the other property that might be interesting about this is a property in which these two versions of the sine function differ. And it looks to be stated in a very different way from injective, but they're very closely related. If the domain, sorry, not domain, codomain, I ate a huge meal right before I came in here, so I'm kind of like in half food coma. If the codomain of F is the same as its range. Just take a second and think about what that means. What does it mean if the codomain and the range of the function aren't the same? The codomain of F is the same as its range. F is said to be onto, this was the English version, coming from the English mathematicians or whatever, or surjective. So what does this mean? You might state this in a different way. What am I really saying with this statement? The codomain and the range are the same thing. They're aimed, right? No. So, this is a statement about the codomain, which is where the outputs could reside, right? I think you raised your hand.
Yeah. The set that like the outputs could reside in has all the outputs in it.
It does have, it always has all the outputs in it.
Only has all the outputs.
It only, right. Everything, yeah, everything in this codomain, everything that's in the set of possible outputs, something does map to that. Yeah. So this is the world in which they could live. And if it's surjective, then there's nobody else that lives in that world besides the people that are in the range, the outputs that are in the range. All right. Finally, if F is both injective and surjective, then it's said to be, I use the French words for both of these. The English term for having both of these is one-to-one and onto. They just say both of them together. So that's the English term for it. The more common one is bijective. Or that F is a bijection. So what does a bijection do? Everything over here maps to something unique over here, right? So we can take everything over here and you can find its exact copy over here, its pair that it's matched up with. You can also go in the other direction because there's nothing over here that is left on its own, right? That's left by itself. So everything that's over here you can map back. So there's a perfect pairing between one set and the other. I gotta be careful I don't get off track. And actually talk about. Okay, these are important properties of functions. And these are properties of functions that are independent of what domain and codomain we're talking about. So no matter what your input is, no matter what your output is, you can always talk about, is it injective, is it surjective, and is it both, one or the other, or neither. Right? That's a property of every possible function. Now we'll talk about functions where it depends. It depends on what the domain and codomain are. So remember the special operations. This is a class about vector spaces, matrices, vectors, vector spaces, and so what we care about are functions that have something special about them in relation to them being functions between vector spaces. So I'll first talk about, well, what kind of functions are we going to talk about in this class? We're going to talk about functions that go from Rm to Rn. These are the only examples of vector spaces that we've seen in this class so far, so these are the ones that we're going to use. Every single vector space we saw was some Rm, for some choice of m, or, well, I'm just saying the same thing, but I'm pointing somewhere else. Every vector space that we've seen in this class is some Rn for some n. Whole number, positive whole number, yeah, positive whole number, not zero either. So some set like this. This was, Andrew was the only one who emailed me about the little challenge question about what is the span of the empty set. Here's something else to think about, and I think that was a good answer. The span of an empty set, we say it's linearly dependent. If you can write some linear combination of the vectors in it that's equal to 0, where the weights are not all 0, you can't do that because you can't write any linear combination at all. So we should say it's linearly independent. We also, I think we had this discussion maybe after class of the idea that if you look at the span of a set, it can be linearly dependent. If you start taking vectors out, eventually you will get to a point where it's linearly independent. So this kind of makes sense that as the number gets smaller and smaller, you eventually cross a threshold where they become linearly independent. And this is another way of stating that. It's saying, well, what if there are no vectors at all? If that trend continues like we should expect it to, then it should be linearly independent. That's just saying that it would be nice if it was linearly independent. It's not saying it's true. So we should be careful. But here's the challenge. What vectors are in the set R0? If it's a vector space, what does it have in it? So that's another weird thing to think about. We don't talk about that in this class. Oh, so R1, this is just R, right? With one exception. So vector spaces, what was special about them? What were the special operations that we can do in a vector space? What can we do with vectors? We can look at them, we can admire them. What mathematical operations can we do with them?
Add and multiply.
We can add, we will be careful.
Multiply by a scalar.
Yeah, exactly. We can add two vectors together as long as they're in the same vector space. And we can multiply them by a scalar. So our scalars are coming from R. So in R, we can add and subtract, we can multiply, we can divide. All of the things that we can do in R, with all of the sort of intermixing them, works in the way that we expected it to. When we write R1, we have the same elements. Exactly the same things. There's 0, there's 1, there's pi, there's square root of 2, there's negative 5 million. All of that stuff is in both of these sets, right? But when we write this, the same way we were saying about the type of the function is something intrinsically connected to it. The type of this thing is, I don't know if I should say this, but it's called a field. It's a number system where you can do addition, subtraction, multiplication, and division of everything, except you can't divide by 0. Other than that, you can divide by anything. As distinguished from what? The integers. You can't divide 3 by 2 in the integers because you don't end up with another integer, right? You have to have a bigger number system. Here, we only have addition and multiplication, scalar multiplication. I'm going to write it as a dot. So if we think of this as a vector space, then we can only do vector space things. If we want to do multiplication of two real numbers, well, it's really the scalar multiplication. All of the things that we're multiplying by scalars are really the same things. Division, we're doing scalar multiplication by an inverse. So there's some relationship between these two things, but they're not exactly the same thing. Here we're talking about R the field. Here we're talking about R the vector space. So this multiplication and this multiplication kind of correspond in the obvious way, right? Subtraction, addition and subtraction really are the same thing. Because 1 and 2 in here, if we identify that with the 1 and 2 here, it's just a real number as a vector. To distinguish them, we might write 1 plus 2 equals 3 for this, and 1 plus 2, the vector 1 plus the vector 2 equals the vector 3 for this. And 2 times 3 equals 6 gets translated to the scalar multiple of 2 of the vector 3 is, sorry, somebody was thinking that, I can tell, is the vector 6. So that's the distinction between the two. It's purely formal. When we do the calculations, we do them in the exact same way, right? But formally, when we say this thing, we're talking about a vector space. When we say this thing, we're talking about a field. more, it's like what we talked about. Intuitively, when you think about these things, you really think about them as being the exact same thing. When we want to be precise, and we want to be able to talk about these things in a mathematically precise way, and we have to be sure that we're being precise about what we mean by these verbs. Okay. So what was special about vector spaces is that they have addition and they have multiplication. So the special property of a function relative to vector spaces. If it's special to vector spaces, then it should preserve all of these relationships that depend on the operations that we can do with vectors. We can do addition, we can do scalar multiplication. So these functions should preserve them. The special property, that's not the end of the sentence, is preserving addition, vector addition, and scalar multiplication. Now in symbols, what does this mean? If f is our function, then when we add two things together, we add two vectors together, we get something. What we map them to, when we add those together, they should add to the same thing that we would get if we mapped their sum over. How do I write this? F of u plus v equals f of u plus f of v. Make sense? The structure of what things add to is preserved. We take two things, if we add them here, and then we add them here and then we map them over, we get the same thing as if we map them over and then add them. Right? The structure of whatever we map over stays the same. It doesn't get destroyed. The other is the scalar multiplication. So C is a real number, U is a real vector, and this maps to what we would get if we first mapped the vector instead of scaling it first and then scaled it. So we scale and then map, or we map and then scale, nothing changes.